Hello, teacher and everyone. So today, me and my teammate will present about the project, which is talk about CPU scheduling algorithm simulator. And for our team is team 9. So for the next, we will talk about the project object and our team member. So our project object. So we interactive simulations. So simulation will like to show the exactly how an operating system of CPU scheduler make it in real time task decisions. Like instead of analyzing static, so we use the formula from the academic textbook, and the user can like define the customer process table and instantly see how the different from parameter execute dynamically. For our team member, we have four members. They are Bong Minh Hiến, Chi Lai Huang, and Nhâm Phạt Đá, and also Yên Minh Ly. And next mainly we'll present about the architectures and code workthrough.
Hello, now move on to my part. I mainly and I will be doing the architecture and code walkthrough. This part will be doing the breakdown of the project architecture, the page structure, and tech stack component. And after that, it will be the core algorithmic representation. For the technology stack and page 8, we use the core development, we use the Java 17 and the to manage with the Maven. This setup will give us the robust and structured workspace, and it uses the dependency to manage completely automate local compilation. Anyone pulling this project can run it instantly without any complex environment setup at all. And then to the visual presentation. For this part, we will use the JavaFX to pair with the Canvas API. Instead of the static element, it will handle the UI dynamically in real-time parameter adjustment and switch between the tabs seamlessly and then render it beautifully to align with the Gantt chart. In real time to use the precise canvas rectangle. And for the page layout, to keep the project maintainable, we structure the code into the clean page layout where any algorithm will store in the separate page where we have the common page. It will hold the hour-based process and the scheduler process. And then in the algorithm page, we use the modular strategy pattern. It will have the distinct class for each schedule, link logic. And then for the gun page here, it is to manage the exact spatial calculation and the time visualization of the project. And then for the UI container, it will contain all the interface and widget, manage all widget and layout. And now to the walkthrough of subtest remaining time, or SRT. The SRT is operated on the preemptive algorithm variant of the subtest job first, or SJF. Instead of letting the process run to completion blindly, the scheduler will continuously evaluate the ready queue on every single clock tick loop to ensure that the CPU is always running the job closest to the finish line. And inside this code here, this is to execute the strict four-step loop on every cycle. We have the step here where the first step, we advance the global scheduler timeline to clock by 1 tick. And afterward, for the step 2, the system will scan for any arrival queue and then move the ready process into the active state where it will be running. And then for the third step, it is the core logic that will select the process to display the smallest remaining execution window. As for finally the step 4, the system will decrement that process and the process remaining time by 1, and the output is the corresponding slice to the Gantt chart that will render in the engine. And now to the walkthrough of multi-level feedback queue. For the multi-level queue setup, unlike the simpler algorithm, our MLF queue here we implement the implementation configures 3 discrete queue that will working to dynamically distribute the process so-called based on the process historically behavior. In here we have the 3 queue where we have the queue 0, the highest priority of all or round robin queue with the timer with a time quantum of 2 ticks. And for the queue 1 here, this is the medium priority of all queue with the time quantum of 4 ticks. And then for the third queue of queue 2, this is the lowest priority. We will have first come first serve SCFS queue with no boundary, with no quantum boundary at all. And as for its behavior, the intelligent MLF queue comes from 3 queue mechanics that we implemented: the demotion hook, priority preemption, and the aging mechanic. For the demotion hook, if the heavy job is expanded its entire quantum bit slice without finishing, then it gets pushed down to a lower queue. And as for the priority preemption, the newly arriving high priority test will always intercept the lower execution pool. This will keep the system highly responsive. And then lastly, the aging mechanic. This process will process the waiting more than the 8 ticks that are from upward to prevent the starvation. If the process is slower, the queue it means that if the process is sit lower queue waiting for more than 8 ticks, it will automatically promote upward to ensure that it will eventually get a CPU time. And now move on to main hearing part where he will do the live demonstration.
So moving on to our next part is demonstration. So we will run our simulation together and also observe and analyze the result together. So for the input setup, we have a sample scenario before I show you the demonstration. I want to show you that we have a standard scenario matrix, a scenario that has 4 processes, and each process has a different arrival time and burst time. And also for the configuration for the round robin quantum, we configure to a 2 tick, and the multi-level feedback queue allocation for Q0 is 2 tick, Q1 4 tick, and Q2 is first come first serve. And the output matrix, it will generate all 5 Gantt chart for all 5 algorithms, and also it will have a line comparison between the average waiting time, average turnaround time for all 5 algorithms. So now we move on to the simulation demonstration. So here, as I told you before, we have a sample scenario, and we can also add more process and remove it, and also load the sample scenario and here for the config. So when we run the simulation, it will generate the Gantt chart for all 5 algorithms. Here you can see, and this is the matrix for all the waiting time, turnaround time for each process, and this is the comparison between all 5 algorithms. So that is all for my part. Moving on to my friend.
So for what we talk next is about like matrix comparison results. So in this table we compare like the performance of all 5 CPU scheduling algorithms like by using 3 matrix average. waiting time, average turnaround times, and average response time. So look at the result that we show, and it is short remaining time or SRT. It is achieved the best waiting and turnaround performance, which is an average waiting time of 5.0 ticks and an average turnaround times of 10.5 ticks. And this is happened because of SRTs always execute the process with the subtask remaining execute time, and it also allows the short job to finish earlier. So for response time, MLF2, it performed the best with 1.5 ticks, followed closely by turnaround robin, which 2.0 ticks. This algorithm gives new or interactive process CPU time very quickly, and which improve the responsiveness. For overview of the matrix comparison result, the results show that decisions that it is difficult algorithm exist in different areas. SRT is the best for minimizing waiting and turnaround time, while MLFQ and round robin provide the fastest response for newly arrived process. For next part is about analytical finding, or we can call it why. So now let's look at why this algorithm perform differently. So firstly, SRT eliminates the waiting matrix because it always selects the process with the shortest remaining execute time, and this allows the short process to finish quickly instead of waiting behind longer one, reducing both average waiting times and turnaround time. On the other hand, like CFS suffer from what is known as the convert effect. So like if the long process arrives first, every short test process has to wait until it finishes, which increase the overall waiting and turnaround time. So for response time and round robin and also MLFQ performance, it is performing better than because they also allow every process to arrive CPU time shortly after arriving. Round robin achieved this by dividing CPU time into the small time slice, while MLFQ improved on this by giving higher priorities to new and interactive process and gradually moving long-running process to lower priority quick queues. So this design difference explain why SRT is the most efficient for waiting and turnaround time, while MLFQ and round robin provide the fast response time. So that's all for my part. Go pass through to my teammate.
Hello teacher, my name is Panda, and now my part is to carry on to the challenges. So during this project, our team faced several challenges. The first challenge was putting all the scheduling algorithm into one simulator, and each algorithm worked differently, so we had to make sure they all work correctly in the same system. The second challenge was the SRT scheduling. The simulator has to check the remaining time of every process at every tick. If a shorter job arrived, the CPU had to switch to it immediately. Another challenge was multi-level feedback queue. We had to make sure a process only moved to a lower queue after using all of its times quantum. If not, the scheduling result would be wrong. We also faced the problem of starvation. Some low priority processes could wait for very long times. To solve this, we added an aging feature. If a process waited too long, its priority was increased, so it could get CPU times. By solving these challenges, we learn more about how CPU scheduling works in real operating systems. And in conclusion, each scheduling algorithm has its own benefit. FCFF is simple and easy to use, and FJS and XORD can reduce waiting times. Round robin improve fairness by giving each process a chain to run, and priority scheduling allow important process to run first. However, multiple level give the best overall performance because it combines different priority levels and can adjust priorities automatically. And thank you for listening. We are ready to answer any question. Thank you.